In the linked video, we took a closer look at solid solution alloys, where the two components are completely soluble in each other in the solid state. In this video we look at the other extreme, where both components are completely insoluble in the solid state. Such alloys are also known as mixed crystal alloys. Again, only binary alloy systems consisting of only two components will be considered. If the atoms of the alloying elements can occupy neither regular lattice sites nor interstitial sites in the base lattice of the host material, the different atoms cannot be arranged in a common lattice structure. This is the case, for example, when the alloying element has a different lattice type or completely different chemical properties to the base material. During solidification, the atoms are displaced from each other's lattice. Each type of atom then forms its own crystal structure, so that there are no atoms of the alloying element in the lattice of the base material and no atoms of the base material in the lattice of the alloy component. While the components are initially completely miscible in the liquid state, they are segregated during solidification. The structure is a mixture of completely different crystals. This is why this type of alloy is called a mixed crystal alloy. Let us look at such a type of alloy using the example of a bismuth-cadmium alloy. As already explained in the video on solid solution alloys, pure substances usually show a constant temperature during solidification. The section where the line of the cooling curve is horizontal is called thermal arrest. For bismuth, the solidification temperature is 271 degrees Celsius, and for cadmium it is 321 degrees Celsius. However, when the two metals are mixed in the molten state, the cooling behavior changes. For example, if 20% cadmium is added to bismuth, the cooling curve will show a period where the cooling is slowed down and a period where the temperature remains constant. While the point at which the cooling curve begins to flatten indicates the start of solidification, the solidification process ends in a thermal arrest. Therefore, bismuth-cadmium alloys generally do not solidify at a specific temperature but within a temperature range. Other alloy concentrations show similar behavior in principle. However, depending on the alloy content, solidification starts at different temperatures, but always ends in a thermal arrest at the same temperature. Furthermore, when looking at the cooling curves, it is noticeable that at a certain alloy concentration, the alloy solidifies only at the thermal arrest. In order to clearly show the cooling behavior of the entire bismuth-cadmium alloy system, the phase diagram is first created from the selected cooling curves. The procedure is the same as for the phase diagram of a solid solution alloy. This is done by plotting the cooling curves on a concentration temperature diagram and again marking the start and end of solidification. In this way you will eventually get two characteristic lines again. The upper lines mark the start of solidification. They correspond to the liquidus line. The lower horizontal line marks the end of solidification and corresponds to the solidus line. Let's interpret the phase diagram in more detail in the following. It can be seen that the liquidus lines decrease from the respective pure substances. Obviously, the onset of solidification is shifted to lower temperatures by the presence of the other substance. The descending liquidus lines eventually meet at a common point. This point is known as the eutectic point. An alloy with this composition is also known as a eutectic alloy. It has the lowest solidification temperature and, unlike other alloys, only solidifies at a constant temperature. The solidus line, on the other hand, is always at the same temperature of 146 degrees Celsius, regardless of the alloy concentration, with the exception of pure materials, and thus marks the end of solidification for all alloys. The solidus line is often also referred to as the eutectic line. The actual solidification process takes place between the solidus and liquidus lines. In this region, parts of the alloy have already solidified while others are still liquid. It should be noted that in mixed crystal alloys there are two two-phase regions, to the left and right of the eutectic point, whereas in solid solution alloys there is only one two-phase region. The phase diagram of a mixed crystal alloy therefore differs fundamentally from that of a solid solution alloy. So note, while the lines in the phase diagram of a solid solution alloy mark a lenticular two-phase region, the lines in a mixed crystal alloy form the letter K rotated by 90 degrees. In the following we will take a closer look at the microstructure formation of different alloys. We start with the example of the eutectic alloy with 40% cadmium. Starting from the molten state, cooling leads to a reduction in the kinetic energy of the bismuth and cadmium atoms, with the substances initially preventing each other from crystallizing due to their very different chemical properties. The solidification temperature of the alloy is therefore lower than that of the pure materials. In terms of temperature, The onset of solidification coincides with the end of crystallization in the phase diagram. Eutectic alloys therefore solidify like the pure substances at constant temperature. When the temperature has finally dropped to the eutectic point, the supercooling has progressed so far that both substances now begin to crystallize simultaneously, but each separately. Due to the strong supercooling, very many nuclei have formed and the structure crystallizes very fine-grained. Each nucleus or growing grain consists of either pure bismuth atoms or pure cadmium atoms, because in mixed crystal alloys the two components are insoluble in the solid state, which means that the individual atoms cannot arrange themselves in a common lattice structure, but form their own grains. Because the atoms are relatively slow due to the strong supercooling during solidification, they can only travel short distances. This usually results in fine lamellar crystal growth. This is why the grains of a eutectic alloy often have a lamellar structure rather than a round shape. This fine-grained phase mixture of finely dispersed bismuth and cadmium crystals is called eutectic. Due to the very fine microstructure, eutectic alloys generally have very good strength and toughness values. This is because the movement of the dislocations is hindered by the fine lamellar structure. The lamellae act as obstacles for the dislocation movement. In addition, eutectic alloys have the lowest melting point of the entire alloy system. This makes them ideal for casting or soldering. After all, the lower the processing temperature of a casting material, the lower the demands on the mold. Furthermore, eutectic alloys do not solidify within a temperature range but at a temperature point, so that the shrinkage can be kept to a minimum. Shrinkage refers to the reduction in volume during the transition from the liquid to the solid state. Let us now look at the formation of the microstructure of an alloy that lies to the left of the eutectic point. Such an alloy is also known as a hypoeutectic alloy. Specifically, we will consider the hypoeutectic alloy with 15% cadmium. In principle, non-eutectic alloys show both a flattening section and a horizontal section in the cooling curve during solidification. Obviously, different atomic processes take place within these sections. These will be discussed in more detail in the following. Above the liquidus line, the alloy is initially completely liquid. When the liquidus line is reached, nuclei form in the melt and the solidification process begins. At first, however, only the base material bismuth crystallizes out of the melt. Crystallization of the alloying element cadmium is completely suppressed. The bismuth nuclei grow into larger grains as the alloy continues to cool, as more and more bismuth atoms from the melt attach themselves to the already solidified lattice structure. Note that these crystallites are made up of bismuth atoms only. Cadmium will not be able to dissolve in the bismuth crystal structure due to the insolubility of the components. Since bismuth is obviously the first to crystallize from the melt, these crystals are also known as bismuth primary crystals. So note, in hypoeutectic alloys, only the base material of the alloy crystallizes out of the melt in the two-phase region to the left of the eutectic point. These are called primary crystals. As cooling continues in the two-phase region, more and more bismuth atoms from the residual melt attach themselves to the already existing crystals. As a result, the concentration of bismuth atoms in the residual melt decreases and the cadmium content of the melt continuously increases. As explained in the video on solid solution alloys, the chemical composition of the residual melt can also be determined from a phase diagram in this case. This is done by first drawing a horizontal line at the current temperature up to the liquidus line. At the point of intersection, a vertical line is drawn to the concentration axis and the cadmium content of the melt is read off. In this case, the residual melt at 200 degrees Celsius consists of approximately 20% cadmium and correspondingly 80% bismuth. The phase diagram can also be used to determine the chemical composition of the primary bismuth crystals. To do this, the horizontal line must be drawn to the phase boundary of pure bismuth, which lies at 0% cadmium, since pure bismuth is present there. The primary crystals obviously consist of 0% cadmium. This is not surprising, of course, as these are bismuth primary crystals, which are 100% bismuth. With further cooling of the alloy, it can be clearly seen in the phase diagram that the cadmium content in the melt increases due to the crystallization of bismuth atoms. For example, the cadmium content of the residual melt at 175 degrees Celsius has already risen to around 28%. The cadmium content in the residual melt thus approaches more and more the eutectic point with 40% cadmium. Finally, at 146 degrees Celsius, the residual melt has just reached the eutectic composition of 40% cadmium. The melt now solidifies like the eutectic alloy previously considered. The melt begins to solidify at a constant temperature to form the eutectic. This means that finely dispersed crystals of bismuth and cadmium are formed. After complete solidification of the residual melt to the eutectic, the crystallization process is completed. In the solidified state, the microstructure is finally made up of the primary bismuth crystals that have previously been precipitated and the eutectic that has just been formed. Let us now look at the formation of the microstructure of an alloy that lies to the right of the eutectic point. Such an alloy is also known as a hypereutectic alloy. Specifically, we will consider the hypereutectic alloy with 80% cadmium. The microstructure formation of a hypereutectic alloy is similar to that of a hypoeutectic alloy. The only difference is that primary crystals of pure cadmium are the first to crystallize out of the melt. The precipitation of bismuth is completely suppressed. So note, in hypereutectic alloys, only the alloying component crystallizes out of the melt in the two-phase region to the right of the eutectic point and form primary crystals. As cadmium precipitates from the melt, the cadmium content in the melt decreases accordingly. This can again be illustrated by projecting the intersection with the liquidus line onto the concentration axis. For example, at 200 degrees Celsius the cadmium content in the melt has already dropped to 52%. Finally, at 146 degrees Celsius, the melt has a cadmium content of only 40% and has therefore reached the eutectic composition. The residual melt now solidifies to form the eutectic. In the solidified microstructure of the hypereutectic bismuth-cadmium alloy, the primarily precipitated cadmium crystals are embedded in the eutectic. Let's look again at the hypoeutectic alloy with 15% cadmium at a temperature of 175 degrees Celsius. The state point is in the two-phase region, so parts of the alloy are still liquid while solid primary bismuth crystals have formed. We have already explained how we determine the chemical composition of the melt and the primary crystals. It is also possible to determine the mass fraction of melt or primary crystals, which means what percentage of the alloy has already solidified and how much is still liquid. To do this, we hang the vessel with the melt sieved and thawed on the liquidus line and the vessel with the already solidified bismuth primary crystals on the opposite side at 0% cadmium. As with solid solution alloys, the phase fractions of mixed crystal alloys are determined using the lever rule, which states that we can determine the respective phase fraction by the ratio of the length of the opposite lever arm to the total length of both lever arms. In the present case, lever arms with lengths A equals 15 and B equals 13 result. The mass fraction of bismuth primary crystals is now determined from the ratio of the opposite lever arm B to the total lever A plus B. With a mass fraction of 0.464, 46.4% of the total alloy mass has thus already solidified. The proportion of melt is therefore 0.536, which means that 53.6% of the alloy is still liquid. This phase fraction can also be determined using the lever rule. For this purpose, the opposite lever arm A is divided by the total lever arm A plus B. In this way, the aforementioned 53.6% phase fraction is obtained. Let us now consider the state immediately upon reaching the solidus line. In this state, the melt has just reached the eutectic composition. The mass fractions of the melt and the primary crystals can be determined using the lever rule as shown. So just before the eutectic is formed, the melt accounts for 37.5% and the primary crystals for 62.5%. The melt now solidifies at a constant temperature to form the eutectic. The phase fraction of the melt thus becomes the microstructure fraction of the eutectic. When fully solidified, the eutectic represents 37.5% of the total microstructure, while the primary crystals represent 62.5%. So note, to determine these microstructure fractions in the solidified state, the distance between the state point and the eutectic point must therefore be used as the lever arm. In this context, the difference between phase and microstructure is very important. A phase is a state of a substance characterized by a uniform chemical and physical structure. A microstructure, on the other hand, refers to regions with specific physical properties that can be defined microscopically, such as individual grains. For example, although the eutectic is a microscopically visible microstructure component with certain physical properties, it does not have a uniform chemical structure. The eutectic is therefore not a single phase, but a mixture of phases consisting of finely distributed bismuth crystals and cadmium crystals. The precipitated primary crystals, on the other hand, are both a microstructure component and a phase. Therefore, the phase boundaries are relevant for the determination of the phase fractions, whereas the microstructure boundaries are relevant for the determination of the microstructure fractions. In the case of the eutectic, the microstructure boundary is at the eutectic composition of 40% cadmium. Let's summarize the microstructure formation of mixed crystal alloys using the example of the bismuth-cadmium alloy system. Although the microstructure in the solidified state basically consists of a mixture of cadmium and bismuth crystals, different microstructures result depending on the alloy composition. In eutectic alloys, the microstructure consists entirely of the eutectic, a very fine mixture of pure crystals of the respective components. In hypoeutectic alloys, the primary precipitated crystals of the base material are also present in the microstructure. In hypereutectic alloys, the primary precipitated crystals of the alloying component occur in addition to the eutectic. It should be noted that as the alloy concentration approaches the eutectic composition, the grain size of the primary crystals decreases. This is because the alloy concentration is already close to the eutectic point. Therefore, only a small amount of primary crystals will precipitate to reach the eutectic composition for complete solidification. The microstructure fractions, that is the proportion of the eutectic or primary crystals, shift linearly with a change in the alloy composition due to the lever rule. For example, the pivot point of our imaginary balance scale for a 20% cadmium alloy is exactly in the middle of the entire lever. The solidified microstructure thus consists of equal proportions of bismuth primary crystals and eutectic. With increasing cadmium content, the equilibrium shifts more and more in the direction of a higher proportion of eutectic. At 40% cadmium, the microstructure finally consists of 100% eutectic. Conversely, a reduction in the cadmium content leads to a shift in the equilibrium towards a higher proportion of primary crystals. Finally, at 0% cadmium, the microstructure no longer contains any eutectic, but consists of 100% bismuth crystals. There is thus a linear relationship between the cadmium content and the corresponding microstructural constituents. Below the state diagram, the course of the microstructure fractions is shown. In this way, the proportion of the respective microstructural constituents can be determined directly from the alloy concentration, even without calculation. Such a representation of the microstructure fractions as a function of the alloy concentration is also referred to as a microstructure diagram. As an example, an alloy with 30% cadmium is considered. According to the microstructure diagram, 75% of the microstructure consists of eutectic and 25% of bismuth primary crystals. Conversely, the required alloy concentration for a desired primary crystal content can also be determined from the microstructure diagram. If, for example, the solidified microstructure is to consist of 25% primary cadmium crystals and thus 75% eutectic, the diagram gives a required alloy concentration of 55% cadmium. Primary precipitated crystals play an important role, for example, in the casting of engine blocks for combustion engines. A hypereutectic aluminum-silicon alloy is used there. The primary precipitated silicon crystals are very hard and wear-resistant, so that the piston rings can slide on the cylinder surface. Not only are engine blocks usually cast, but mixed crystal alloys in general are usually cast due to their special casting properties and are therefore referred to as cast alloys. However, due to the presence of two phases, the microstructure is relatively inhomogeneous and has limited suitability for cold forming as stress peaks can occur at the phase boundaries, leading to cracking. In contrast, solid solution alloys generally have a homogeneous microstructure because the components are completely soluble in one another. Solid solution alloys therefore generally show better forming properties and are therefore also referred to as wrought alloys. Finally, a note on the phase diagram. The phase diagram shown gives the impression that adding very small amounts of cadmium, even a few atoms, causes an immediate shift in the end of solidification from 271 degrees Celsius for the pure substance to 146 degrees Celsius now. This is because complete insolubility was assumed. In reality, however, cadmium atoms are always soluble in bismuth to some extent. Therefore, starting from the pure substances, the solidus line does not drop off immediately in reality, but gradually transitions to the eutectic line. This diagram is ultimately a first step towards the phase diagram of alloy systems, whose components are partially soluble in each other. We will look at these types of alloys in more detail in another video.